Welcome to X-Maths. My name's Lee, and today we are going to work on consolidating your grade 12 trigonometry, which means, of course, we're going to go back and revisit some of the sections we've done previously, namely our compound angles and double angles, and our, hopefully, 3D trig if we get a chance to. We are going to see now how we go, but let's start first of all by looking at it. Let's just remind ourselves of a few of our formulas. Right, so if we have a look here at our grade 12 trigonometry, it's all centered around compound angles. And we had a whole series of equations that resulted from it, but these eventually developed into what we called double angles, which are just offshoots of our compound angles. So let's have a quick revision on that. Let's start with the first formula that says the cos of A minus B is. Now remember, I said to you to remember these formulas rather than to rely on your formula sheet. The formula sheet is fine, but if these formulas are in your head, it's just that much easier to identify what you have to do. So let's have a look at these formulas, and remember there were shortcuts I showed you. Right, if it's a cos, we always go cos, cos, sine, sine. The angles are A and B, so we go A, B, A, B. And for a cos formula, we always have the opposite sign to this, so this would be a plus. So using a similar principle then to get the formula of cos A plus B, we know it's cos, cos, sine, sine. We know that this will be an A, and this will be a B, and this will be an A, and this will be a B, and this sign will be a minus because it must be the opposite one to that. Right, so now we go and we look at the sine formula. Now remember with sine, we go sine cos, and the sine, S-I-G-N, is always the same as the one in the bracket. So let's have a look. So let's take sine A minus B, and we know it's going to be sine cos. Now we know that A will belong here and B there, which means here it must be B, A. So where this is a sine A, this will be a sine B. This is a cos B, that's a cos A. And remember we said the sine will be the same. So let's quickly look at this one, which is sine A plus B. Now again it's sine, cos. The angles are A, B, so here it's going to be B, A. And the sign will be the same, so it'll be a plus sign. Now, these are what we call our compound angles, and from there we derive our double angle formulas. Now, really, it's easy to work them out. In the previous session, we did look at how we get those answers, so I'm going to take it as assumed that you understand how to do this. Perhaps you can go back and look at your notes and remind yourself how we actually came up with these formulas. Right, so let's write down what they are. Let's change color so we stress it. If we're looking at sine 2a, there is only one formula for it. It's 2 sine A cos A. But cos 2a has got three different formulas. The first one is cos squared A minus sine squared A. The next one is 2 cos squared A minus 1. And the third one is 1 minus 2 sine squared A. So right, knowing these formulas is always the best way to go. So now knowing these formulas, what we're going to do now is we're going to go and examine certain kinds of questions that can be asked using them. We have done some before in the previous session, but these are just a few more to polish off the section as such. Right, let's move to the question. Now this is a very popular question we're about to do, one that you've seen in grade 11 already, but of course it didn't have your compound angles in it in grade 11. So this is a good opportunity for us to quickly revise the concepts you learned in grade 11. Right, this question says, if cos 20 degrees is m, so that's our given, write each of the following in terms of m. Now, what I like to do with these questions is I like to start by drawing a little triangle representing the situation cos 20 equals m. Now, it's not necessary for every question, but it is very useful when you get down to the harder questions. So I would look at this and I'd say, I know by definition that cos 20 degrees equals m over 1. And cos, by definition, is your adjacent side over your hypotenuse. Now, what do we know about 20 degrees? 20 degrees is firmly in the first quadrant. So there would be my 20 degrees. This would be my right angle. The adjacent side would be the one down here, and the hypotenuse is the one opposite the right angle. So what is missing is this value, which is actually my y value. Now, of course, as soon as we see a right-angled triangle, we know we can solve this by using the theorem of Pythagoras. So we can say, let's call this y, so we know that m squared plus y squared equals 1 squared. So y squared is equal to 1 squared is 1, and this one transposed will be minus m squared. So y is equal to the square root of 1 minus m squared. Remember, I did stress this previously in other sessions, but remember, whatever you do, this is definitely not equal to this. I'm going to spend some time just quickly showing you why that is again, because this is such an important concept, and if you're going to get confused on this, it can cost you lots of marks in an examination. Let's go over here and look at something we know. We know that 25 minus 9 gives me 16, and the square root of 16 is 4. Now, if it's true that that happens, this would be 5 minus 3, and of course 5 minus 3 would give you 2. Are those answers the same? Most definitely not. So whatever you do, you may never, ever, ever, ever square root over a plus or a minus sign. It is really not a possibility. You may square root over multiplication and division. And if you look back to our exponents and surds section, you'll see that we actually do that with multiplication and division. Right, so let's clear this off. And let's go back to what is correct rather than what is wrong. And let's see if we can solve it out. So we know that, and we've now got this drawing, so we can replace this with the square root of 1 minus m squared. Now, as I say, it's not necessary for every single one of these questions, but it sure makes our life easier when we get to some of the harder ones. Right, let's start with A. A asked me to work on the cos of 340 degrees. Now, a good idea with this kind of question is always to reduce the angle first. And we reduce using our normal reduction. So we use our 180 minus, our 180 plus, our 360 minus. We avoid our 90 minus and our 90 plus, our 270 minus 270 plus, because in actual fact that just makes life complicated. So our first reduction is always using our 180 minus, 180 plus, 360 minus. So in this case, this is going to be 360 minus. So it's equal to 360 degrees minus 20. And from our reduction, we know that that will be positive cos 20 degrees, which means this drawing is not needed at this stage because we know that the cos of 20 is just m. So the first question, relatively easy and straightforward, no problem at all. Right, let's look at question B. And let's just change our color so we're clear what question belongs where. Right, B talks about the sine of 110 degrees. Now, I know a lot of you are thinking to yourself, well, the easiest way to get 20 degrees here is to go 90 plus 20, and you are right. But of course, as soon as you use 90 plus 20, you've got to worry about the fact that it's in the second quad, that the 90 will change the ratio, and all sorts of things. So I suggest that you rather, let's work with 180 minus. So doing that, I know that this will be the same as saying 180 minus 70. Now remember, this step need not be shown. It's really your choice whether that step's there or not. But in the second quadrant, I know that sine is positive, so it's equivalent to the sine of 70. Now, why I think this is a better way is you know that 70 and 20 add up to 90, and sine and cos are co-ratios. So that means it's as simple as changing the one to the other. So at this stage, I can say that 70 becomes a 20 as long as I change this to a cos. What I'm actually doing here is I'm saying this is the same as saying sine 90 minus 20. 90 minus 20 is in the first quad, so we don't have to worry about sines, and the sine will change to cos 20 because of that 90. Right, so that brings me to the end of that question, and of course it's really easy now because it's cos 20, so it's m. So far, this drawing I've drawn has served no purpose yet, but I can guarantee you it will certainly prove its worth in a little while. Let's go to the next question. Right, the next question is also not too bad. It talks about, let's find the value of 1 minus sine squared 70 degrees. Okay, now remember the priority here is always to get a 20 degrees there, because the 20 degrees will enable me to use that substitution. Now that's not a problem, because we've just discussed that this could become 20 if this ratio changed to cos. So that's what I'm actually looking at, which is perfect, because now I would go 1 minus, and of course the square means square whatever cos 20 is. So you could have written it rather like this. So that's the same as saying 1 minus m squared, and that question is complete. Right, so far again, no need to use that drawing I've done. So let's go on to question D. Question D says the cos of 40. So let's take another color. Let's go to D, the cos of 40 degrees. All right, well, 40 degrees. How on earth are we going to get 40 degrees to be 20? Well, we've just done this whole section on double angles. And so from double angles, we know that 40 is 2 times 20. And so there's nothing wrong with me going over here and going cos 2 times 20 degrees. Of course, remember I'm using the fact that this is what I'm looking at. And of course, we've got a choice of 3 formulas here. But what do we have the value of? We have the value of cos 20. So cos 20, it makes sense for me to choose the formula. So let's go back there. It makes sense for me to choose this formula, because in this formula I only have coses, which means my drawing is still not needed for this question. If I had chosen this one or this one, then I would have had to use my drawing. But we can still avoid it, so let's avoid it for now. All right, let's go down here. And so we know we're going to use the formula 2 cos squared 20 degrees minus 1. Formula 2 cos squared 20 degrees minus 1. So that's going to be 2, and we know that this is going to be m squared minus 1. Good, so we're still working perfectly all right without that drawing. Right, so let's go to E now and see what E brings. Let's get a color again. Okay, E says, what is the cos of 50 degrees? Right, let's bring the screen up a little bit. And we are at last going to get to use this drawing. Now, how can I know that for sure? Well, let's show you. The cos of 50, well, doubling it won't work, because 2 times 20 is 40. That's not going to be good enough. But I can see that 50 could be written as 30 plus 20. So I could go along here and say this is the same as saying the cos of 30 degrees plus 20 degrees. And the moment I do that, I go to this one over here, and I can see that this would be the formula I would choose to use. Because here I can expand now, separating the 30 and the 20, which is a good idea, because the 20s I can use my drawing for, 30 is a special angle. So let's go back to the question. Okay, so we're going to write this as cos 30, cos 20, minus, because remember the sign's different, sine 30, sine 20. Right, so the cos of 30, no problem. We know from special angles it's root 3 over 2. The cos of 20 is no problem. We know it's m. The sine of 30 is a half, but now we hit our problem. The sine of 20 degrees. Now, nothing you do can make that into a cos 20 degrees other than to use your square identities, which is quite hard work, or alternatively, using my drawing. So if we go up to my drawing, I know that sine, by definition, is my y value over my r, or my opposite over my hypotenuse. So there's my opposite. So I'm going to take the square root of 1 minus m squared over the hypotenuse, which is 1. And now it's not so bad, because all I would do is I say, well, it has a common denominator of 2. So it's root 3m minus the root of 1 minus m squared. So right, now you can see why that drawing was quite useful. Right, now you can see that what we've done here is we've used double angles to sort this one out, and we've used compound angles to sort that out by breaking it into 30 plus 20. So it's a nice combination of using our matric work in with our grade 11, and you can see that we wouldn't have been able to do these two questions last year. This is definitely matric level work. Right, let's move to the next question. The next question talks about simplify without using a calculator, sine 50 over times cos 15 times sine 15 over cos 140. Now remember, we've talked about without using a calculator and said that in actual fact it's essential we show every step. Obviously we can zip this in the calculator and get an answer in 2 seconds flat, but it's really not a wise move if they've said without a calculator, because that is going to give you 0 for the question. So what do we do instead? Remember, we don't have to use our calculator. We are absolutely fine to use our special angle diagram. And I'm sure you remember from previous sessions, I recapped this for you. This coordinate is 2, 0. This one is root 3, 1. This one is root 2, root 2. And this is 1, root 3. This one is 0, 2. And the radius is always 2, 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So it is quite possible without the calculator to engage with this question. Right, so what do? We look at this, and the first step must always be to reduce our angles to acute angles. Because once they're acute, it's simpler to actually identify where to go to. While they are a mixture of acute and obtuse angles or reflex angles, it's really difficult to identify a pattern. Right, so let's pick up another color pen. And over here, do you agree with me that the sine of 50 degrees will stay just that? The cos of 15 will stay just that. And the sine of 15 will stay just that. However, this 140 can be replaced with 180 minus 40. And the moment I do that, I can see that in the second quadrant, cos is negative. So this will become minus cos 40 degrees. Now, as I said to you, once we do that, it really makes life a lot easier. Because you can see 40 and 50 add up to 90. If they add up to 90, we're dealing with co-ratios. So it is possible to lose those by using our co-ratios. So let's do that. I'm going to leave the sine 50 alone. And I'm going to leave the cos 15 alone. And the sine 15 alone. And what I am going to do is I'm going to change this. So it's over and negative. Now I know if I make this a 50, because it adds up to 90, this cos will change to sine. Remember, the procedure is actually cos 40 equals cos of 90 minus 50. And then from our reduction, that is sine 50. Now that's very good news, because now I can cancel or divide that into that and get rid of it. So I'm left with minus cos 15 sine 15. Oh my goodness, 15 degrees. How on earth are we going to work with it? Well, if you've learned your formulas, you're smiling now because you're saying to yourself, well, I've actually seen a formula very similar to this. The formula that I've seen that's very similar to this looks like this. Sine 2 theta equals 2 sine theta cos theta. The problem is that I only have this part. I don't have the 2. Now that's not a problem. If you remember back to our identities, sometimes it was a good idea to times by a convenient form of 1. And this would be a case like this. So what I could do is I say, let's times by 2 over 2. Now do you agree with me that if I'm timesing by 2 over 2, it's actually timesing by 1, so nothing has changed. But it does enable me to do this. Now that is very good news, because now I have this formula. It doesn't matter if these are written the other way around, because remember, if I say 2 times 3 times 4, it's the same as saying 2 times 4 times 3. So this now would become minus, because the minus has got nothing to do with this formula. And this would change to sine 2 times 15 degrees. And yes, we still got the 2 at the bottom there, but that's no problem. 2 is just a number. Now, of course, what is 2 times 15 degrees? 2 times 15 degrees is 30 degrees, and 30 degrees is one of my special angles. So this is very good news indeed. So let's pick it up from there. So this is minus sine 30 degrees over 2. Now, if we're using our drawing, the sine of 30 degrees is over here, and sine by definition is the y value over the r, which means in actual fact I have minus a half over 2. Of course, we can just use our calculator to get that value, but I am trying really hard to be good. So this is equal to minus a half times by, now of course we invert this bottom fraction and multiply, and we end up with minus a quarter. A really nice answer, nothing wrong with it. Okay, so I think we've recapped nicely the simplification. The very important fact we have dealt with here is the fact that if we have sine theta cos theta, we can always times by 2 over 2 in order to use the formula sine 2 theta. That is well worth making a big highlight around because it's actually a very useful technique. Let's put a cloud on it so you can remember it. Very, very important technique. Helps you out in a lot of cases. Right, let's look at the next work. Now remember I mentioned to you we had done identities. Yes, we had, but I want to just polish them a little bit more and just deal with a few more complicated examples just so that you are feeling more confident about the section. This is an extremely important section in the matric final. Right, so we don't need to say much about it. We've basically dealt with it. Perhaps we can just give ourselves a quick summary, reminding ourselves about the rules we did last time. The first thing we said is we always start with the side with the most complicated angles. So we start with the side with the most complicated angles. Now this is a bit different to what we did in grade 11. In grade 11 we chose the most complicated side. Here we're choosing the most complicated angles. So a 2 theta is more complicated than a theta. A theta plus 30 is more complicated than a theta. And so this is how we make our choices. So right, the next thing we would have done is we would have followed all the rules of grade 11. So our grade 11 rules, which basically involves expanding, because yeah, we've got the compound angles. Then we would look for what I call the ugly sisters. And there's 3 of them, remember them. There's sine squared theta plus cos squared theta equals 1. We've got sine squared theta equals 1 minus cos squared theta. And we have cos squared theta equals 1 minus sine squared theta. If there were no ugly sisters, we would then look for tan. And we would change tan to sine theta over cos theta. And then we would do basic algebra. Now remember, basic algebra means factorize, work with fractions, etc. And then we would recycle back to this point if we haven't got anywhere, and hopefully we'd get out. And if we didn't, there were 2 emergency measures, which I'm not going to recap here, but there were 2 emergency measures on your grade 11s, which we did discuss when we last did the section. So let's move to the question now and see what we're looking at. This one says to me, prove the identity that cos A times cos minus A plus sine 180 plus A times tan A is equal to cos 2A. Well, if we look here, 2A is pretty complicated, but 180 plus A is even worse. So let's start with the 180 plus A side, so the left-hand side. Now the first step here is to try and get your angles to look as simple as possible. So cos A is as simple as it gets. However, this one over here, we know that minus A is actually over here in the 4th quadrant. And remember, we've got our little summary that tells me in this quadrant only cos is positive. So this would become cos A. Right, then we've got plus. Now this guy is a straightforward reduction. It's 180 plus A, so we're talking here. And in the 3rd quadrant, sine is negative. So it's negative sine A. And we've still got our tan A. And we can close the brackets. Right, so what have we done? We've reduced them now all, and we can now look for our ugly sisters. Do we have a sine squared plus cos squared equals 1 or any of the others? And the answer is no, not yet. So definitely the next step called for now is to change our tan to sine over cos. So we have cos A. Over here I have cos A. That minus times the plus is a minus. We can make that sine A. And tan A will change to sine A over cos A. Okay. Now, remember, the next step is to use basic algebra. So basic algebra says, let's write this thing as one fraction. So it's going to be sine squared A over cos A. Basic algebra then says to me, let's take a common denominator here. So we have cos A, and over here we can go put it all over cos A, and it's going to become cos squared A minus sine squared A. Sure, this is looking good, because now I can see that this cos A and this cos A divide out, leaving me with cos squared A minus sine squared A. And of course, because you've learned your formulas, you already know the answer of this. You know it's going to become cos 2A, which is clearly the right-hand side. And so we finished the question, and there we are. You could, of course, have left it there, gone to this side and expanded it. But you know what? That's so easy. And if you've known your formulas, you may as well just go straight to the cos 2A. So right, nice question. Again, I just ran through how we used our rules. Let's move to the next one. Right, now in question 4, it says, prove the following identity. The tan of theta equals 1 minus cos 2 theta over sine 2 theta. Now remember, I said to you, we look for the side with the most complicated angles. 2 theta is more complicated than theta. So we are going to start on the right-hand side. Right, now, what do we know? We know that tan is sine theta over cos theta. You might say, well, Lee, why are you doing that? I thought you said we start on the one side. Yes, we do. But I'm bearing in mind that at the top of my fraction, I would really like a sine theta. The bottom of my fraction, I would really like a cos theta, because then I've got the problem solved. So why am I doing this? I'm doing this so I can easily choose which is the correct formula to use for cos 2 theta. So right, over here I go, and it's 1 minus cos 2 theta, and I have to make a choice. The sine 2 theta, there's no need for a choice. There's only one. So it's 2 sine theta cos theta. Now remember, we've got 3 formulas for this. The first one says that it's cos squared theta minus sine squared theta. The second one says 2 cos squared theta minus 1. And the third one says 1 minus 2 sine squared theta. Now if I look over here, I can see that if I want to get a sine, then the best one to choose would be this one, because then I've got sine in the top. Okay, I could have chosen any of these in actual fact. It wouldn't have made a difference. But it just makes it easier for me if I choose the right one to make life simple. So I'm going to put in 1 minus 2 sine squared theta. Right, now why is that good news? Well, let's have a look. We now have 1. That negative is going to distribute in, so it's going to be minus 1 plus 2 sine squared theta all over 2 sine theta cos theta. Right, good news. That 1 and that 1 are going to fall away, 1 minus 1 being 0. And now I'm left with 2 sine squared theta over 2 sine theta cos theta. And of course, here I can see the 2 will divide into that 2. And one of these sines will cancel with one of those. And look at that. Isn't that magnificent? We've got sine theta over cos theta, which is clearly equal to tan theta, which is equal to the left-hand side. So quite a nice way to go about it. And what I'm trying to do here is to teach you to think about the outcome. Just by the way, there is another way you can make the correct solution here, or correct selection. You would say to yourself, if I've got a 1 minus something, it's always a good idea to have the 1s fall away. So if I look at the first formula, if I put that in, 1 would not fall away. If I put that in, 1 also wouldn't fall away, because the minus would make that a plus, so I'd pick up a 2. But if I put this one in, the 1s will fall away. But I think it's easier to bear in mind how it must look at the end. Right, so let's now go and look at another question of it. So far, hopefully I've taught you 2 useful things for the future. Right, this one says prove that sine A plus B minus sine A minus B is equal to 2 cos A sine B. And then the B part says hence. Now, I want you to always watch out for this word. When you see hence, you know that it's directly related to this top thing here. Okay, so we are going to use what we did in A to solve B. Right, so let's look at A. A is straightforward. It's just a straightforward theory question, really, because it's just using your formulas. The most complicated side would be the left-hand side. And so we're going to start by expanding that. So we're going to say this one here becomes sine, cos, sine, cos. The angles are A and B, B and A, and the sign must be a plus. Then we go over here, and remember this is minus this whole thing. And this one expands to sine, cos, sine, cos. And again, it's an A and a B and an A. And this time the sign in the middle is a negative. Right, so this is equal to the sine of A, the cos of B, plus the sine of B, the cos of A, minus the sine of A, the cos of B, and of course that minus times that minus is going to give me plus sine of B, cos of A. Now the good news is this one and this one will fall away because one minus the other one falls away, so we're going to get 2 sine B cos A, which is equal to my right-hand side. Remember, this was actually my left-hand side, so I was a little bit naughty going into it without saying that. All right, not too bad. We are now ready to go into the B part. Remember, the hence part has to have something to do with this top part. Now it says hence or otherwise. Or otherwise means if you went another route, that would be fine, but they're obviously not going to make it easy for you if you do that. The idea here is that the A part gives you a clue or a hint on how to handle the B part. So let's go to the B part. If they didn't use the word otherwise, so if that hadn't been there, then you would have no choice but to use the A part. But since they gave you a choice, you do have a choice, but I'm going to still use the A part. So what do we know from the A part? We know that the sine of A plus B minus the sine of A minus B is equal to 2 sine B cos A. And the thing they want me to prove now is that the sine of 3x minus the sine of x is equal to 2 cos 2x sine x. That's what we're required to prove. That's the abbreviation I'm using here. Right, so I'm going to start on the left-hand side. And what I'm going to try and do is match, let's just put it in another color, match these sides. So I would say to myself, right, this sine 3x must be something plus something. So let's try 2x plus x. And this one must be something minus something. And if we use the same two angles, I'll get 2x minus x. Now you can see that's good news because it's fitting that pattern. In other words, I'm letting A be 2x and B be x, which means I can go straight to the side. I can say 2 sine x cos 2x, because that was sine B cos A. Right, so now we're ready for it. Let's see whether it's what we wanted. Well, yes, it certainly is. Look at that. Remember, I talked to you about the fact that if we're multiplying, the order does not matter. So this is absolutely the same as that, which is equal to the right-hand side. Now you can see that by giving you that little hint by that first part, it made it very easy for you to get the second part. However, as I've said to you, if it says otherwise, you're welcome to use any other method as well. But just know that they've given you that hint for a good reason. All right, let's move to the next question. Now this one looks slightly more complicated. It says prove that tan x equals 1 minus cos 2x over sine 2x, which of course you have just done. And hence deduce this. So I'm not going to go through how to do this again because we have done that in the question 4. But I'm going to use this part and hence deduce. This is the important part, that the tan of 22.5 degrees is equal to that. Well, hence means using what was above. So we have tan x equals 1 minus cos 2x over sine 2x. And we want to hence it. So we want tan of 22.5 degrees. What are they telling me? Well, I think you can see that they're telling me that the x would have to be 22.5. So when I go over here, I'm going to go 1 minus cos, and instead of going 2x, I'm going to go 2 times 22.5 over sine 2 times 22.5, which gives me 1 minus cos 45 degrees over sine 45 degrees. Now 45 degrees is a special angle, and we've got that drawing if you want to use the drawing, or you can use your calculator to pull up what the value is and just put it in. So I know it off by heart, so I'm just going to be lazy now and say, well, I know that cos 45 is root 2 over 2, and sine 45 is also root 2 over 2. Right, so now basic algebra comes in, and I say to myself, at the top I can take 2 as a common factor. That means that's over 1, so it's going to be 2 minus root 2 over root 2 over 2. Right, which then becomes 2 minus root 2 over 2 times by 2 over root 2. The good news here is we can do a bit of cancelling. We can say that 2 divides into that 2, and we're now left with 2 minus root 2 over root 2. Right, back to the question. Let's see what they were actually asking you to prove. They were asking you that, and you can see your answer does not match. Now, what's going to happen here is you need to either rationalize or simplify that fraction in some other way. So let's go back to it, and I'll show you that you can actually do it in one of 2 ways. Right over here, we could say 2 minus root 2 and divide individually into each one of these. So that's option 1. So that's the tan of 22.5. Right, so here you can see that that would be the same as saying root 4 over root 2 minus 1. And root 4 over root 2 is going to become root 2 minus 1. So that's option 1. Nothing wrong with that. But you also have the option of rationalizing. Now what we do for rationalizing is we times by a convenient form of 1. In our session on surds, I think I did mention this to you. So we would times by root 2 over root 2. Now doing that, we would times it in there, so we're going to get 2 root 2 minus root 4 all over root 4. And of course that's 2 root 2 minus 2 over 2, because the root 4s can become 2. We can take out the 2 as a common factor, leaving me root 2 minus 1 over 2, and that 2 divides into that 2, which then gives me the same answer as this side. This was a bit easier, I think, but it's actually a choice. So all I wanted to demonstrate to you here, that if they introduce a number and you've just proved an identity and it says hence, you just do the substitution of that number in place of the variable that you've just proved. So not a bad idea to work with that. Right, now last time in Trig we also touched on trig equations, and I talked to you about several ways to do it as well, but there were 3 definitions that I said were really worth knowing. So I'm going to recap them and then show you some typical metric trig equations. So let's have a look at the 3 equations first of all. Right, let's look at trig equations now. We did handle them before, but I would like to just summarize them again and go through some typical metric level equations. Right, let's quickly run through the 3 things. Let's just check we've got, yeah, color pink. Right, so now we know that the first definition we need to know is that if cos theta equals A, very important that A is an element of minus 1 to 1, then theta equals plus or minus shift cos A plus K 360 degrees, K an element of Z. In other words, this K is integers. Why? Because the normal period of a cos graph is 360 degrees, and normally the amplitude of a cos graph, or not normally, always, cos graph, will be between minus 1 and 1. Right, let's remind you of the second definition. The second definition talked about the sine of theta equaling A. Once again, A was an element of minus 1 to 1. And we know that theta will equal shift sine A plus K 360. Again, the 360 because the period of the sine graph is 360. Or theta equals 180 degrees minus shift sine A plus K 360. And remember again, we have to qualify K in elements of Z. And then the last one is the tan definition, which says if we have tan theta equals A. Good news, A can be absolutely anything. Why is that? Well, if you think of a tan graph, remember it starts and it goes like this forever and forever down. So it's not restricted like, say, a cos graph, which would look like that, or a sine graph, which would look like that. So here you would get your 1 and your minus 1. Here you get your 1 and your minus 1, but this one, no restriction at all. So theta would equal shift tan A plus K180, remembering that the period of a tan graph is 180 degrees. Now, using these three definitions, we're going to go now and look at some typical matric questions. Right, over here, it says determine the general solution to the equation, and there are 5 of them there. Now, what I'm going to do is I'm going to go through each one, and each one has a certain kind of personality. And if you know what that personality is, you're never going to have problems with this section. Now, this very first one, I think you can see is clearly connected to our compound angles. And as it stands, 54 degrees is not a special angle, so it's not going to be fun to work with. But we can see that this is one of our formulas that we learned. And hopefully you can see that that is the formula cos 54 degrees. And remember, it always has the opposite sign to that, so it'll become a minus. X equals sine 2x. Now, at this stage, this question becomes relatively easy. What I want you to notice is there are certain characteristics here, other than the reduction we've just done. This over here is a different angle to this one. So if I like, I can say its personality is that the angles are different. And there are no coefficients. Now remember, coefficient is the number written in front of a variable. So in this case, it would be a number outside this trig ratio. So no coefficients. As soon as I see that, I use 90 minus to solve. All right, now you might be saying, well, what are you on about? Let's show you. Right, so what are we doing here? We got cos of 54 degrees minus x. Now, my advice to you is, when you have a choice of changing your ratio from a sine to a cos or a cos to a sine, always go from sine to cos. Why? Well, if we go back to our previous little summary over here, look how much easier that little formula is to remember than the sine one, which has got 2 parts. It's not wrong to choose the other one, but it's just so much easier if you choose the one that makes your life easier. Right, so let's pull it down. And over here, I'm going to change this from sine 2x to cos 90 minus 2x. Now, of course, that is a straightforward use of the cos 90 minus theta equals sine theta. That's the theory I'm using over here to do that. So I just go 90 minus that angle. Right, so back to the question. Now, once I'm here, I can see that I have the same angle, same ratio on both sides, different angles. So according to my definition, I can go 54 degrees minus x equals plus or minus 90 minus 2x plus k 360, k an element of z. Of course, we know we're near finished, but it's the start. Now, I think you can see clearly the similarity between this and this formula that I had just now, where I said that is equal to A, and then I said, well, theta is equal to plus minus. There's the plus minus coming out. Shift cos A, well, of course, we don't need to shift because we've already got it where they are both causes, and plus K 360. So you can see clearly this would work. Right, so what do we do next? Well, we split this into 2 separate solutions. So we say the one solution will be 54 degrees minus x equals minus 90 minus 2x plus K 360, or 54 degrees minus x equals 90 degrees minus 2x, because that's the positive one, plus K 360. We have already qualified that. So we don't need to explain any further. Right, so now we're going to actually go and solve these. So starting over here, we're going to tidy this up. So we're going to say it's 54 degrees minus x is minus 90 plus 2x plus k 360. That means I have minus x minus 2x, because I'm transposing that, is minus 90, and I'm transposing that, minus 54 plus k 360. That means I have minus 3x equals, now if I do this, I'm going to get minus 144 plus k 360. Now at this stage, I have to divide everything by minus 3, and by everything, I mean even this. So this is going to become x equals, a negative negative makes a positive, 3 into 14 goes 4 times, and into there, into 24 it will go 8 times. So it's 48 degrees minus k 120. Now if I go minus k 120 or plus k 120, it really does not matter. Because remember, k is an integer, and whether I am working with it as a positive or a negative would make the sign change. So it really doesn't matter if I wrote plus k120 or I wrote minus k120. If you're more comfortable because it's following the rules of what we normally do, the minus is absolutely fine. Right, so to the next side of the question, let's look at this one. This one says 54 degrees minus x is 90 degrees minus 2x plus k 360. So now that would become minus x, transposing that, it becomes plus 2x. That's 90, and transposing that, it's minus 54 plus k 360. Now that means that x equals 90 minus 54, which is 36 degrees, plus k 360. Let's just check, that's, yeah, perfect. Right, so there's your two solutions for this cos graph. I didn't give you a restriction over what area we want to work, so it really doesn't matter how I write them. I can leave them in this form, and I have already qualified k in element of z. If I said to you, give me solutions from minus 360 to plus 360, well, then we'd have to go and use our calculator and generate the answers. One of them I will do like that, just so you can see how it works. Right, so that's the first question. Very, very simple and very straightforward. Just remember the procedure and the identification. The first procedure was we recognized that that needed to be shrunk to that. Then we saw that we had different angles, no numbers in front, and so we went the 90 minus root. That's like the trigger for that one. Right, let's look at the next one. The next one says 4 sine x plus 3 cos x equals 0. So let's go down the page. Right, now let's work on to B, and let's have a look at the personality of this particular question and how we will handle it. So let's have a look at it. Let's get a highlighter and let's look. What is the first thing I did in the previous one? I looked at the angles. Well, look at this. This time the angles are the same. And the second thing I looked at is, do we have a coefficient? And yes, we do have. So it's actually got a completely different personality to the previous question. So let's write down what it's saying to me. First of all, the angles are the same. And we have coefficients. Now, the moment that happens, the approach we use is we divide through by cos. Now, at this stage, I know that you're probably feeling a little bit apprehensive because you've always been told by teachers, never divide by a variable. And in all effect, cos x is a variable. So let's just talk for a few seconds on that. Quite right, if I had x, say 4x squared plus 3x equals 0, I would never, ever in my whole entire life do that, because I know that x could equal 0, and if it did, which it actually does do, that would make the whole thing undefined. So yes, we may never do that. However, here, when I divide by the cos x, so now I'm going to say, let's divide this one by cos x, this one by cos x, and this one by cos x. in effect, what I'm doing is I'm changing the ratios from sine and cos to tan, because now it becomes 4 tan x plus 3 equals 0. So if you want to think about it very simplistically, you could say to yourself that dividing by the cos is in fact contained inside the ratio tan. So effectively, you haven't lost the value of cos, which you would have done had you divided by the x. That x equals 0 wouldn't have been a possible solution. You would have lost it completely. So we can do it with this ratio because in actual fact, we're changing the ratios we're working from, sine and cos, to tan. And so it's a completely different thing. Right, so once we're here, we can see that this now becomes relatively straightforward. So we have 4 tan x equals minus 3, and so tan x equals minus 3/4. And now it's time to finally pull up this calculator and work with it. So let's just go and get it. There it is. Now remember, the definition of this said that if I want to solve for x here, I go shift tan. So let's press in shift tan, and we want to go minus 3/4. So minus 3 divided by 4, close my brackets, equals, and there you see your angle coming up. Now, I haven't stipulated to how many decimal places we're working, so let's assume we're working to 1 decimal place just for convenience. But of course, in an exam question paper, they would have said somewhere either at the start of the paper in the instructions or in the actual question how many decimal places you should be working to. So right, over here, I'm going to say that's negative 36.9. So x equals negative 36.9. In fact, let me write that a little bit more clearly. Negative 36.9 degrees plus k 180. And remember, we always qualify k an element of z. This is what we call the general solution. If you don't remember from last time, but that is what it is. And so if they'd say nothing about what restriction we're working on, we always assume that we're giving all solutions, which is the general solution. Right, so that is the quality of that particular question. You can see it was the exact opposite of the previous one. Now, if we look at C, we can again see that our angles are different. And we can also see that there are no coefficients. So that is fitting the quality of the first one, except you haven't had to retract it. So that makes it a little bit easier because there's one less step, but basically it's going to follow the same procedure as the first one. So let's just remind ourselves, the first thing we had with the quality of it was that the angles were different. No coefficients. And because of that, we use our 90 minus. Now, I've deliberately chosen this one a bit different to the first one, in that you're going to see we're going to get a negative, and I'm going to teach you a really nice way of avoiding problems with a negative, because that negative can be problematic if you happen to put it in the wrong place. Now, first of all, I will always try and keep my cos 2x on the left-hand side. So I leave my cos 2x here, and I would bring across this, which was of that form. Now, if I didn't do that, if I wrote sine x plus 30 degrees equals minus cos 2x, all that would happen is I would have had to times both of these sides by negative 1 to move the negative off the cos. And I'll explain to you why we need to move it off the cos in a moment. Now, do you remember when we were working in our quadrants? This was where minus theta was. And minus theta being in the fourth quadrant means that if it was the cos of minus theta, it would have been positive cos theta. So we don't have a nice way to get that negative out of the way by bringing it in there. But if I had sine of minus theta, well, that's really nice because in the fourth quadrant, sine is negative. So that's why it's easier to have it on that particular value than on the cos. So let's get rid of the unnecessary work here so we don't get too cluttered. Let's get rid of that. And this bit of explanation here because we don't need it. And certainly that because we don't need it. Right, let's go back to the question. Right, so as I've said to you, we can now go cos 2x equals, and this can become sine, and we can bring this negative into the bracket. So it's minus x minus 30 degrees. Great. Now the negative is no longer a problem. And now what we have to do is we have to make sure that we have a cos on each side. Remember, I talked to you about using sines fine, just a bit more difficult, so it's always better to change to cos. So what I'm going to do now is I'm going to go here, and I'm going to say this changes to cos, as long as I make this 90 degrees minus that package, which is minus x minus 30 degrees. And I've still got the cos 2x over here. Right, let's bring ourselves down a bit. And what I'm going to do is I'm just going to shift this question down so we've got a bit more room to work. Right, so over here now, we're ready to go. We can make this a little simpler. We can go the cos of 2x equals the cos of, and we can simplify this bracket. So it's 90, that minus minus makes a plus x, and that minus minus makes a plus 30. Which means I have cos 2x equals the cos of 120 degrees plus x. Now it's of the form cos something equals cos something, which means I can now use my definitions as such. So I can now say 2x will equal plus or minus the angle I had here plus k 360. Remembering to qualify that k is an element of z. Right, now we split it up into two solutions. So we can go 2x equals the negative of that, which is minus 120 minus x plus k 360, or the positive of that angle, which is 120 plus x plus k 360. Tidying up, we got 2x plus x equals minus 120 plus k 360. And again, I think we just need to move this out a little bit more. Seems like this question is taking a lot more room than I initially anticipated. So 3x is equal to minus 120 plus k 360. Now, of course, we don't want that 3 there. We're solving for x, so we divide this by 3, and, of course, that by 3. So x is equal to minus 40 degrees plus k 120. Right, lovely. Now let's go to the other side. Here we've got 2x, and we transpose this over as a minus x equals 120 plus k 360. And this one's going to be ever so slightly simpler because we're immediately getting our x, and that's what we've got. Again, as a general solution, I have qualified that k is an element of z, and so really all I have to do now, if I was asked over an interval, is generate the answers, but they don't ask me that, so that's the end of the question. So this one is almost identical to the first one we did. A and C are very similar. The only difference is A, you had to do one extra step and you had to reduce it down using your compound angle formula. Right, let's see what the characteristics are of the fourth one. And the fourth one now, you're going to see things are a little bit different. So let's extend our page. First of all, we see that our angles are there and they're not the same. Now immediately we see that if there had been no coefficients, we would have used 90 minus. But bad news is there are coefficients. Now, if there are coefficients and the angles are different, this is the case where we expand to solve. Don't be too quick to expand. This is the only case that this would happen in. So let's have a look at it and summarize the characteristics. Right, angles different. And coefficients on the ratios. Therefore, expand. In other words, we're now going to use our expansion for sine x plus 30 degrees over here. So we're going to go 2, open brackets. This is going to be sine cos. Oops. Let's just tidy that up a little bit. Cos. Remember, this is x, and this is 30 degrees. This is 30 degrees, and this is x. And the sign will be the same. It will be a plus, and that is equal to 3 cos x. Nothing to do there. Now, I can see over here I've got special angles. And I know that the cos of 30 is root 3 over 2, and I know the sine of 30 is a half, whether I use my calculator or my drawing. So it's 2. This is going to become sine x times root 3 over 2 plus a half the cos of x equals 3 cos x. Now, fortunately for us, there's a 2, which means I can times the 2 into each of these terms, and it'll make me lose the denominator. If it didn't, it wouldn't have been the end of the world. I would have just times through by the denominator a bit later on. But fortunately for me, in this case, that's the easy way to go. So it's root 3 sine x plus cos x equals 3 cos x. Well, what can we see? We can see that we have got some like terms. So we can go root 3 sine x equals 2 cos x by bringing this one over the equal sign. And now we can see we're back to that number b. The angles are now the same, but there are coefficients. And how did we handle that particular type? We divided this side by cos x and this side by cos x. So we're going to get root 3 tan x equals 2, which means the tan of x equals 2 over root 3. Right, lovely. Now we can go and use our calculator. So let's pull it up. And of course it's tan again, which is quite nice. Let's just clear it. We can go shift tan, and we're going to go 2 divide by root 3. Spacebar out, remember, close the brackets, equals, and I get 49.1. So this will be x equals 49.1 degree plus k 180 degrees, k an element of z. And that's how we would get it. Right, so now we're ready to move on to the fifth and last one. And I must say that this fifth and last one, I don't think there's a great chance you're going to get it. And I do believe that if you do get it, they're going to help you a bit. But I'm going to just teach you to recognize its personality, so if they don't do that, you're going to be absolutely fine. So let's move to the next question, which I've put on a new page. And you can see this looks a bit different. Well, first of all, we look at what the characteristics were. We've got the same angle, which is good news. We've got a coefficient in front there. But what we've got that we never had before is a number like that. And that causes the complication. So the angles are the same. There is a coefficient, but there's also a number. So what are we going to do with this question? Let's just tidy it up a little bit. Now I've decorated it so beautifully. Okay, let's go over here. As soon as I see this, the technique I am going to use is to divide it through by 2. So up here we go. I'm going to divide this by 2, this by 2, and this by 2. Of course, I haven't changed it if I divide right the way through by the same thing. So we're absolutely fine with this. But what I can do is reshuffle it so it looks a little bit more user-friendly. So I could go root 3 over 2, which hopefully you recognize, and I'm going to come back to that in a moment, plus a half sine alpha equals a half. Right, so now if I go over here, I'm hoping that you've realized that's a special angle and that's a special angle. And what I've got to try and do is get it to be a special angle of either cos or sine, but I like to work with a cos formula. The cos expansion for me is the easier one to work with. So what I'm going to do is I'm going to say what would cos be to get the answer root 3 over 2? And the answer is it would be the cos of 30 degrees. If you don't believe me, take your calculator out and check me. Make sure I'm telling the truth. Now that means the sine of 30 must give me a half, and you'll see if you do it, you will get it. And now you can see this question is no longer a problem. It's actually become relatively easy because this is an expansion for cos, and it's 30 degrees. Remember, it always has the opposite sign to that, equals a half. Great, so now we're here, and it's really very easy from here because we're going to go, we don't even have to use a calculator on this one because a half is a special angle. So if we go shift cos a half, we will end up with 60 degrees as the answer. Let's just show you just so you are convinced. We would hate you not to be. Right, let's clear it over here. Shift cos 1 divide by 2, divide by 2, close the brackets, equals, and there you see the 60 degrees. Okay, so now you're convinced. Let's go back to the question. And so we know that 30 degrees minus x is equal to plus or minus 60 degrees plus k 360. K, an element of z. Right, so that means that 30 degrees minus x is minus 60 plus k 360, or 30 degrees minus x is 60 degrees plus k 360. Right, so looking at it now, we can say minus x equals, and transposing that, it's going to be minus 60 minus 30, so it's minus 90, plus k 360. Dividing through by negative 1, I'm going to get x is equal to 90 minus k 360. And remember, I did talk to you about the fact if you go plus k 360 or minus k 360, it really does not matter. It's not important at all because k is an integer, and it just means that when you put negative integers, it'll become positive, and when you put positive integers, it'll be negative. Right, let's look at this side. Over here, I have minus x equals 60 minus 30, which is 30 degrees plus k 360. And dividing through by my negative 1, I've got minus 30 degrees minus k 360. Wonderful. So we've actually now got the trig equations well and truly under control. Let's now go and look at when is an identity invalid. Now, you've dealt with when things are invalid in algebra quite considerably. And usually it's to do with denominators that may not be 0 or square root signs that can't be negative. So I would like to just summarize by saying there are 3 considerations whenever we're looking at something being valid or invalid. And the first consideration is the denominator may not equal 0. The second consideration is if I have a square root of something, whatever the something is, the something would have to be greater than equal to 0. It may not be less than 0. So we could have gone squiggle, not less than 0. Okay, and now with trig identities, there's a third one. And that is if we are using the ratio tan. Tan, as you know, has got asymptotes. So obviously, wherever there's an asymptote, we have a problem with tan. So let's say, for example, I said tan squish in this particular question. Then I know that squish may not equal 90 degrees plus k 180, k an element of z. Now there's a reason I've used squish and not theta, because you're going to see this can be as complicated as we like and we can work with it. So just to recap, there are 3 considerations. The denominator may not equal 0, the square root sign must be positive, and if we're using tan, we must exclude our asymptotes. So right, let's look at a question. I think that sort of puts it into perspective for us, and it's actually very easy. Here we have it. Question 8 says, for what values of A is the following identity not valid? Right, let's look. We've got that, and we've obviously proved this identity, so I'm not going there. I'm just going to talk about validity. The first thing I know, the first thing I always look at is the denominator. So the denominator is 2 tan A minus sin 2A equal to 0, and the other denominator is tan A. So when is it not valid? It's not valid when this equals 0 and when this equals 0. Now obviously we have to solve these things. This is a little bit hectic, so let's just go through it slowly. We know that that would become 2 sin A over cos A, and sin 2A is 2 sin A cos A. Right, we can now times through by the cos A, so we have 2 sin A minus 2 sin A cos squared A equals 0. And we can take out the 2 sin A as a common factor, leaving me with 1 minus cos squared A. The good news is, what do we know about 1 minus cos squared? Well, we know it's equal to sin squared A. So in actual fact, we have 2 sin cubed A equal to 0. Right, now if that's so, do you agree with me? I could divide both sides by 2, and I would get that. And I can cube root both sides, so in actual fact, all I'm interested in is that, sin A equals 0. So now all I would do is I would say, well, right, using our calculator, we could actually use special angles, but let's get some practice on the calculator. So it's shift sine 0, close the brackets, equals 0 degrees. So we know that sine is A equals 0 degrees plus K 360, or A is equal to 180 degrees minus 0 degrees plus K 360, which means we have A equals K 360, and over here we have A is 180 degrees plus K 360. Now if we think of a sine graph, we know it would look like this. That would be 360 degrees. Let's just pull this page up a bit so you can see clearly. And you can see that if we looked at where it was equal to 0, it would be there, there, and there. Now if you look at K 360 would take care of this one, and this one would take care of that one. So if you wanted to, we could have put these two into one solution and just said A equals K 180. But you know what? I don't think it's worth thinking like it. Look, it looks very elegant and all that stuff, but I just think it's really hard work to be able to do that. So don't get too worried about that. Right, let's go up here to this one and let's solve it. And over here we have tan A equals 0. So we know that A is equal to shift tan 0 gives me 0 plus K 180. K an element of Z. And by the way, I see I didn't put that there, so naughty me, make sure you do that. And you can see that this is also represented over here. So in actual fact, this could all be summarized into that one solution I've given you at the bottom there. However, it's not a problem if you write them as separate ones, it's quite in order. Right, so let's go back to the identity now and see what else we have to look at. Are there any square root signs? And the answer is no, there are no square root signs. I think there's very little chance of having a square root sign in there. And if you did have it, well, then you just have to deal with it. But I think there's probably about a 1 in 1,000 chance of that happening. So it's not something too important for you. Then it says to me, the third thing, what about tan? So let's look at that. Well, we do have tan. There's a tan and there's a tan. Now, what did I say to you about that? I said that if we've got a tan, whatever the angle is, may not equal 90 degrees plus K 180. Now, the good news is that that one there is a relatively simple solution for all of them. So you don't even have to think anymore, but if you thought of your tan graph, you would remember it looked like this, etc. And you can see here's your zeros. And of course, it would do the same on that side as well. Okay, so that would give you that. Notice I haven't said not equal to, because they said when is it not valid? So the answer is it's not valid here and here. Right, okay, so that takes us through that, and let's have a look at what else we've got here. Let's pull this together now by saying if the question had read an element of 0 to 360, how would we have answered this differently? Well, all we would have done is we would have taken each one of our solutions we obtained and generate the answers over that interval. So let's go back to the answers we got and just write them underneath each other. We have A equal to K 360. We have A equal to 180 degrees plus K 360. From the tan one, we have 0 plus K 180. So A equals 0 degrees plus K 180. And of course, from the asymptote, we have A equals 90 degrees plus K 180. All of these are Kn elements of Z. So let's pull them together now and get a solution. So A would be an element of. Right, let's start with this one. Now, if I got K 360, if K is 0, the first answer will be 0 degrees, and we know that's in the restriction. If K is 1, the next answer would be 360 degrees, and we know that's in the restriction. If we start using negatives, we won't get right answers, so we basically finished with this one. Now this one here, if we let K equal 0, we would get 180 degrees. So there it is. And if we made K equal to 1, it'll be too big for the interval. So we finished with this one. Now here, this is 0 plus K 180. So if K was 0, we would get 0, which is already in place. If K is 1, we would get 180, which is already in place. And if K was 2, it would be 0 plus 2 times 180, which is 360, which is already in place. So this one is done already. Right, so the one that remains is the asymptote. So let's look at that. If we look at this 90 degrees, if we put k equals 0, we're going to get 90 degrees. And if we put k equals 1, we're going to get 270 degrees. So there we have 5 solutions over that interval, and we have used all of these to generate. As you saw, this one was already catered for, so this one would have covered those two. Remember what I said to you? That is those two summarized. And that is exactly the same as that. Right, I hope you've enjoyed being with us today and you've enjoyed the session and you're feeling like you've got your trigonometry a little bit more under control and more clear on what kind of questions you can get asked. Join us again soon and have a great day.